Welcome to the Explainer. Up to this point, we've built a model that totally gets the deep meaning of words thanks to embeddings, but it's hiding a massive, fatal flaw. We have a model that is completely and utterly blind to the order of the words we feed it. Today, we're going to fix that flaw. We're going to teach our model how to perceive time and sequence.
Just think about the difference between the dog bit the man and the man bit the dog. For us, that difference is huge, right? One is a bad day for a person, the other is a bizarre news headline. But right now, our model literally cannot tell these two sentences apart. The core mechanism of the transformer treats everything you give it as an unordered bag of words. The embedding for the word king or dog is identical whether it's the very first word in your sentence or the very last.
To understand why this happens, we have to look at older architectures. Previous models relied on recurrence or convolution. Recurrence basically means a model reads words one after another, exactly like you're listening to me right now. Because it reads sequentially, the order of the words is baked directly into how it processes information. But the transformer is different. To achieve its incredible speed, it throws all the words in at once and processes them entirely in parallel. By prioritizing that raw speed, it completely sacrificed any built-in sense of order.
Because of this parallel processing, the core attention mechanism is what we call permutation invariant. This simply means if you take your input words and shuffle them completely at random, the model will compute the exact same mathematical values, just shuffled around. It doesn't see a sequence of words flowing through time, it just sees a static set of words floating in space.
Think of it like a pile of unnumbered raffle tickets dumped on a table. The model can see every single ticket, and it knows exactly what is printed on them, but it has absolutely no idea which ticket was drawn first, second, or third. To solve this, we must explicitly write a position number on each ticket before it ever enters that pile. We have to manually inject a sense of order.
To write this position number, we create a completely separate vector for every single position in the sentence. Position 0, position 1, position 2, and so on. But here is the crucial detail. This position vector has a very specific size. It uses the exact same mathematical dimension as our word embeddings, a size referred to as d_model, which is exactly 512. By making them the exact same size, the where it sits stamp can be seamlessly combined with the what it is meaning. Okay, let's dive into the math. To fill those 512 empty slots with a mathematical pattern that represents a position, we use a formula that perfectly alternates between two smooth waves. For all the even-numbered slots in our 512-dimensional vector, we use a sine wave. For all the odd-numbered slots, we use a cosine wave. Don't let the trigonometry intimidate you. We're really just generating a pattern.
Within this formula, there are two main symbols we need to decode. First up is pos. This is simply the literal position of the current word in our sentence sequence. So the first word is at position 0, the second word is at position 1, the third is at position 2, and it just counts up from there.
The second symbol is I. This represents the index of the dimension. It simply refers to exactly which of the 512 slots in our vector we are filling at this exact millisecond. As we move down the vector from slot 0 to slot 511, I increases. Now, what is truly fascinating is what happens in the bottom half of this formula. As I grows, as we move deeper into our 512 slots, the denominator gets larger and larger, which changes the frequency of our wave. The early slots in our vector oscillate rapidly, while the later slots oscillate very slowly. The resulting wavelengths form a geometric progression from 2π all the way up to 10,000 times 2π. We aren't just giving the word a single wave. We are giving it 512 different waves, creating a completely unique mathematical fingerprint for every single position.
This brilliantly illustrates the binary counting analogy. Think about how a computer counts in binary. The rightmost bit flips back and forth incredibly fast, 0, 1, 0, 1. The next bit flips every 2 steps. The leftmost bits flip very slowly. These different frequencies of flipping combine to give every single number a unique pattern. Our position formula does the exact same thing, but instead of hard 0 or 1 bits flipping, we use the smooth, continuous flow of sine and cosine waves.
So why go to all this trouble with complex sinusoids instead of just numbering the words 1, 2, 3? Well, the authors specifically hypothesized that this wave structure would allow the model to easily learn to attend by relative positions. Because in human language, relative distance often matters much more than absolute position.
Mathematically, this hypothesis means that for any fixed offset, let's call it k, the encoding at position pos plus k can be written as a linear function of the original position pos. In plain terms, The relationship 3 words apart has the exact same mathematical form whether you're looking at the first 3 words of a sentence or the last 3 words of a sentence.
And here is the next crucial reason for using waves: stability. If we just used raw integer counting, 1, 2, 3, all the way to 5,000 for a long document, the position numbers would grow infinitely large. A massive position number would completely dwarf the delicate numbers inside our word embeddings, ruining the model's understanding of the word itself. Sine and cosine waves, on the other hand, are strictly bounded. They are permanently locked between -1 and 1, keeping the numbers perfectly stable no matter how long the sequence gets.
This perfectly mirrors the hands on a clock. The second hand, the minute hand, and the hour hand all move at entirely different speeds or frequencies. But they never spin off the clock, right? They always stay on the exact same bounded dial. And together, their combined positions name a completely unique exact moment in time. 15 minutes later looks like the exact same shift on the clock face, no matter what time it currently is.
That brings us to a highly unconventional design choice. To combine our word meaning and our word position, you might expect we just attach the two vectors end to end, making a vector twice as long. But instead, the position vector is added directly into the embedding, element by element. This is exactly why they had to share that demodeled dimension of 512.
Now, you might worry that adding numbers directly on top of our word embedding would scramble the word's actual meaning, but think of it like a fixed watermark pressed onto a printed page. Because we're operating in a massively high-dimensional space of 512 numbers, there is more than enough room to lay the position pattern right on top of the text without making the original words unreadable. The model can easily keep the two kinds of information separate.
What's really interesting about this second design choice is how static it is. Unlike the word embeddings, which start random and are heavily trained and updated by the model over time, the position encoding formula is entirely fixed. It's calculated exactly once from that sine and cosine formula. There are 0 learnable parameters here. It's completely identical during training and during inference.
But let's pause for an honest caveat straight from the original paper. We shouldn't oversell these sine waves as pure magic. The authors openly admit they ran an experiment testing a learned positional embedding instead of the fixed math formula, and it produced nearly identical results. They kept the fixed sinusoids mostly because they thought it might help the model extrapolate to sequence lengths longer than anything it ever saw during training.
So, we've solved the fatal flaw. Every single word going into our model is now a complete 512-dimensional vector, perfectly carrying both what it means and exactly where it sits in time. The input to the encoder is finally complete. But this leaves us with the ultimate question, the mechanism everything has been building toward. Now that the words are fully prepared, how do they finally look at each other to form true context?